good morning. How are you today? Okay, well, you are here with me again. อาจารย์ปัทมาพร here in Bangkok, Thailand. Okay, well, the weather in Thailand is getting warmer and warmer. Okay, I don't know how many degrees today, but it's actually feeling very humid and hot. We are getting into our summer now. When I'm doing this, today is first week of March. Okay, first week of March in 2021. Okay, so today we are going to do impedance. Okay, the concept of impedance. Okay, so the definition of impedance is the ratio of the phasor voltage to the phasor current. Okay, and the unit is ohms. Okay, omega, ohms. Okay, so in another word, if I write it, impedance is equal to the phasor of V over the phasor of I, as the definition said, right? So I'm going to find out what the impedance for the elements that we have done, the three elements, a resistor, an inductor, and a capacitor. Okay, so let's start with the resistor, R. Okay, a resistor R. So let's say that you have a voltage source and it's connected to a resistor R. Okay, and this is Vs. Let's say Vs as a function of T. The current flows out of the positive side of the terminal of the source, right? And goes past through R. Of course, there's a voltage drop here, but the voltage drop across R is the same as the source voltage. And if I'm giving that, my Vs of t is simply A cos omega t. A cos omega t. Okay, and if we change this into phasor form, right? Phasor form, it's simply A, right? E to the j 0, right? Because the phase angle is 0, or equal to A angle 0 degrees volt. Okay, so if I want to find a current I, right? The current I, the formula Ohm's law is I of t is equal to Vs of t divided by R. Correct? So therefore, my I of t is simply equal to A cosine omega t over R. And if I change this into phasor form, right? Phasor I becomes A over R angle 0 degrees, right? The magnitude is A over R. Okay. Amps. So by definition of impedance, it's the phasor of the voltage over the phasor of the current equal to, then phasor of voltage across R is Vs, right? So it's A 0 degrees divided by I, right? The phasor I is A over R angle 0 degrees, right? A cancel, R jumps up, so become R 0 degrees ohms. So therefore, the impedance of resistor alone, okay, is R or equal to R 0 degrees ohms. Okay, right? So that's for a resistor. Now let's look at an inductor. Okay, give you a few minutes to write that down. I hope you understand this. Okay, if you do not catch it, you can always pause me and or do the rewind. Okay, move the cursor back and listen again. Next one, an inductor. L. Okay, so again, so let's say you have Vs given to you connected to an inductor L, right? Of course, there's a voltage drop VL here, but it's the same thing as Vs. Okay. I'm going to do it derived in a long way for you to see. First, starting with, of course, our Vs of t is equal to A cos omega t volt. So, well, the formula for the relationship between the current and the voltage for inductor is VL, right? Okay, if I write down VL right here, VL of t is equal to L di by dt, right? Hope you remember that. Okay, so therefore, if my V, if I want to find I, right? Then therefore, I have to write my I of t, right? My I of t that go through L here would be equal to 1 over L integrate A cos sine omega t dt. Right? You want to find I from its relationship here. You want to find I, you have to integrate V. Okay? And V is A cos omega t. Right? This is equal to VL of t in this case. And the answer is A over omega L sine omega t amps. Well, I'm going to convert this, transform this into cosine. So IL of t becomes A over omega L sine omega t becomes A over omega L cos of omega t minus 90 degrees amps. And so now I can change to phasor form, right? The phasor form. So IL phasor form is equal to, okay, I should keep this consistent. So IL right here, and this is IL. So IL in a phasor form would be A over omega L, right, with the phase angle of minus 90 degrees amps. So therefore, the impedance is then in this case VL over IL. VL is, of course, simply A 0 degrees, right here, right? If you put VL phasor, it's equal to A 0 degrees volt, okay, divided by IL phasor form, so it's A over omega L angle minus 90 degrees. A cancel, omega L inverse back up there, so it become omega L angle 90 degrees, 0, right? Because this become 0 minus 90 degrees, so become positive 90 degrees ohms. Ta-da! So this is the impedance of an inductor, omega L angle 90 degrees. Okay, but this is in polar form. This is in polar form. I can change it to rectangular form also. Well, 90 degrees, due to Euler's identity, we did it last sessions, right? Then you know that 90 degrees is equivalent to J. So since 90 degrees is equivalent to J, okay, so therefore we replace that angle 90 degrees with J, become J omega L ohms. So this is the impedance of an inductor. Omega L angle 90 degrees or J omega L. Something you have to remember for the exam. Just think that it's to practice your brain, okay? Practice, exercise your brain by remember formulas. Okay. Also, I want to show you another way of doing this. Okay. Well, we know that the relationship between the current and the voltage for an inductor is V equal to L di by dt, right? L di by dt. Well, we know that if you have d dt, right, in phasor form, you simply put j omega in front. So in this case, if you want to change to phasor form, well, V become a V in phasor form, L, right, d dt, you put j omega in front, and I become I phasor form. So therefore, you have this term, right? Phasor V equal to L j omega phasor I. So therefore, the impedance is equal to phasor V over phasor I. So it becomes j omega L, right? J is equivalent to 90 degrees, so it's omega L angle 90 degrees ohms. Ta-da! Same thing. Ta-da! See? Beautiful or what? Okay, so what does this 90 degrees means? There's this 90 degrees. So for resistor, there's no 90 degrees. It's 0, right? It's the same thing. ZR is the same as R. Okay, but in this, for the inductor, there's 90 degrees angle. So what does it mean? So I'm going to show you right now. Okay, so let's look at the phase relationship. You have VL equal to L dIL by dt. This is the formula. Okay, and let's sketch IL of t. So I have IL of t here, and it's simply sine wave. Okay, sine wave form. I want to sketch VL. Sketch, not just sketch. So you have to be exact. I want to sketch VL. So let's see. Well, if I have, this is 0, right? And I put it as point, this is like position A, position B, position C, position D, position E. Right, this is B. Okay. Right, want to sketch this is 0 still. Well, where we have to differentiate IL. Where is DIL dt at maximum values? So at di dt maximum value is, of course, di dt means you're doing the slope, right? The slope of the function IL. So the maximum value will be the slope, whereas the slope is the highest. So the slope is highest at point A, right here. Positive, in the positive going up, and this one coming down and going up again. So maximum values of di dt multiplied by L, multiply, get bigger. So it becomes maximum point of the graph for VL. So VL's maximum at point A, at point C, but down here, and at point E up here again. Okay, maximum. Where, okay, is DIL dt equal to 0? DI dt at 0. 0 means there's no slope, right? So where is that? It's at the peak. So at the peak here, right? So it's 0 multiplied by L is 0. So that means VL is 0. Ta-da. And right here also, DITT is equal to 0. So multiplied by L is 0. That means VL is 0. So therefore, your graph for VL turn out to be the cosine. Not so beautiful, but the cosine. See that? So there's a shifting between the voltage and inductor by 90 degrees. Okay, and the way we say it for inductor, we say that, well, VL start first, right? VL start first, and IL comes after, start later on, we say that IL lags behind VL by 90 degrees. IL for inductor, IL lags V by 90 degrees, and this is where your 90 degrees comes about. Okay, in the impedance form. Okay, so that's for an inductor. So let's do it for capacitor. Capacitor. Okay, so same thing. So we have VC, this is IC. So the relationship, so let's say that Vs of t here, right? Of course, from the picture, from the circuit is equal to the voltage drop across a capacitor also. And let's say it's equal to A cos omega t again. So that means VC in a phasor form is A 0 degrees volt. Right? Now the relationship okay, between the current and the voltage, the current through a capacitor and the voltage drop across a capacitor is IC of t is equal to C dVc dt. So therefore, if I want to find IC of t, I have to differentiate, right? So C d dt of A cos omega t. And the answer is minus C omega A sine omega t. Change it to cos term, the cosine term. IC of t is equal to, well, minus C omega A sine omega t. It's equal to omega C A cos omega t plus 90 degrees amps. So if you change this to phasor form, the phasor form of the capacitor current would be omega C A angle 90 degrees amps. So the impedance is equals to voltage across C divided by the current through C. So voltage across C is A 0 degrees divided by omega C A 90 degrees. So the answer is A cancel out 1 over omega C angle minus 90 degrees ohms. So in conclusion, ZC is equal to 1 over omega C minus 90 degrees. Change to rectangular form, right? If J is equivalent to 90 degrees, J represent 90 degrees, then minus 90 degrees would be represented by minus J. So it's minus J over omega C ohms. So this is the formula for an impedance for a capacitor. Okay. Of course, you can do it the short way, if you remember. So we have a formula, right? I of C of t equal to C dV of t dt. if you change it to phasor, right? So this is IC to phasor IC equal to C. d dt is j omega, right, in phasor form, and v of t change to phasor v. Vc, maybe you can put Vc here. Okay, so therefore the impedance is Vc over IC, so equal to, what is it? 1 over omega c j, right? If I multiply by j, j divided by j is 1, right? So therefore, but j times j, oh, by the way, j is also, also means square root of minus 1. Okay, in math it's I, right, equal to square root minus 1, but we cannot use I because I for us is current, so we use j instead. So therefore it's equal to j times j is minus 1, so minus j over omega c, right? And minus j is represented by 90 degrees, minus j is minus 90 degrees, so same thing. Okay, same thing. Now, what is 90 degrees? This minus 90 degrees. So let's do, similar to what we did for an inductor. Well, the formula is I equal to C dV dt, right, for capacitor. Right, current go through a capacitor. There's a voltage drop across the capacitor. So therefore, I have to differentiate voltage. So if I have my V here across the capacitor as a sine wave, right? And I want to sketch my current. The current that goes through a capacitor, right? 0 also. Let's line this up, the point for sketching, right? Well, ddt, dv dt at 0. dv dt is 0, right, at the peak. There's no slope, so it's right here and right here. So dv dt equal to 0, times c is 0, so therefore the current is 0, so it's 0 at this point, 2 point. The slope of voltage is maximum, dv dt is maximum is at this point, 0, negative maximum and positive maximum, so maximum, negative maximum, and maximum again. So therefore you get a cross shape for the current. So that means there's a phase shift by 90 degrees again. But in this case, right, I start first, right? For inductor, I comes later. For this case, I start first, so we say that I, the waveform I, leads V by 90 degrees. Okay, so this is where the angle, so there's a shifting, there's a phase shift for inductor and capacitor. And the way you remember this, who leads who or who lags who, okay, is by the word civil for you to remember. Civil, okay. So capacitor, C, right? So the first 3 letters, C, for capacitor. See, you spell it with I come first. So capacitor, I leads V, I come before V by 90 degrees. But for inductor, right, is the last letter, last 3 letter, L right here for inductor, right? But the last 3 letter, it's V first and I comes later. So we say that for inductor, I lags V. So for inductor, I lags V, right? For capacitor, right? For capacitor, it's I leads V. For both cases, I can think I as a very important. So use I as a reference. I come, I first. Go with I first. Okay. So capacitor, I leads V. For inductor, I lags V. But what I learned, from my teacher, my teacher in America, he used the word ice. Actually, Eli the Iceman. So, but in this case, instead of V, we put E in it. Okay. So for L, right, voltage come before I. For capacitor, this is inductor, right? For capacitor, the current comes before V. So I remember the word ice only. Ice, oh ice. Okay, see, I leads. And so if inductor is the opposite. Okay, so that's how I remember it. Okay, but your choice, whatever you want to, how you want to remember this, civil or Eli the Iceman, that's up to you. Okay, or you can find your own way to remember also. No strict rule to that. Okay, so therefore, in conclusions, I'm going to put everything on the table. In a table, this is phasor. And this impedance. Okay, right. So for resistor, okay, the relationship in time domain is, right, V of t equal to R I of t, V equal to IR. So in phasor form, phasor V is equal to R times phasor I. So the impedance, okay, is V over I. So it's equal to R. Okay, ohms. Of course, impedance is ohms. Okay. For an inductor, it's V of t equal to L di by dt. So therefore, in phasor form is phasor V equal to L j omega I. So for the impedance, it becomes j omega L, okay, or equal to omega L 90 degrees. For capacitor, it's I of t equal to C dV by dt. So therefore, in phasor form, it's I equal to C j omega V. So the impedance turned out to be minus j over omega c, or equal to 1 over omega c angle minus 90 degrees ohm. So this is a very useful table for you to remember into the exam. Okay. To the exam. Okay. So from this, I'm going to show you some problems. Okay, some problems. Okay. We're going to analyze some simple problem. Okay. So for example, if we have now not just R alone or L alone or C alone in a circuit, but we have a mix. So in this case, a mix of a resistor and a capacitor connected in series. Okay. And it's given the voltage here is already in phasor form with a frequency equal to 1.5 kHz. Okay. And we want to find phasor I, the current in terms of phasor form. Okay. And I is equal to 2.2 k ohms. And C is 0.02 microfarad. Okay. So to analyze the circuit, you need to change all the elements value into impedance values. So pretty much change everything into ohms unit. Well, R is in ohm unit already, we can leave it. Okay, but C is in farad. We have to change that into ohms unit, which is the impedance. So therefore, we have to apply the formula that we have for the impedance for capacitor, right? So therefore, it's equal to minus J over omega C or minus j over, of course we don't have omega. Omega is not given. It's given only a frequency, but we know that omega is equal to 2 pi f. So 2 pi times 1.5 times 10 to the 3, right? And omega c is 0.02 times 10 to the minus 6. Using your calculator, you need your calculator for this. You need a calculator for this class, period. Okay, a scientific calculator also. Okay, not your mobile phone calculator. Okay, so therefore when you press your calculator, the answer come out to be minus j 5.3 k ohms, or equal to 5.3 k angles minus 90 degrees ohms. Okay, to find the current, okay, to find the current, okay, so the current, whatever you have learned before the midterm, okay, it all applies here. So therefore in this case, your phasor I would be equal to the voltage source divided by the total impedance. Not total R anymore. You know, at the beginning of this course, it was simply R, right? So you add R's up together and get R total. But in this case, we have impedance, Z. So we call it impedance, total impedance. So you have to find total impedance. Total impedance is that these two elements are connected in series. So therefore, it's simply R plus ZC. Okay, so therefore you would get 2.2 minus J 5.3 K ohm. So this is your Z total, right? Well, we have to do divisions. So let's say that you don't have a calculator, you don't have this, you don't know how to convert or use your calculator directly, okay, to do the math with the complex numbers. So that means we have to do division. We have to change everything into the polar form. So therefore, we're going to confirm this set total into polar form. Right now, we have it in the rectangular form. So therefore, your R would be equal to square root of 2.2 k square plus, right? Well, it's minus 5.3 k square. So the answer is 5.74 k ohms. Okay. The angle theta, the phase angle theta, is inverse tangent of y over x. So it's equal to minus 67.5 degrees. So therefore, your so-called Z total is equal to 5.74, right, angle minus 67.5 k ohms. So therefore your current is equal to V is 0 degrees divided by 5.74 angle minus 67.5 degrees K. So the answer is 10 over 5.74 is 1.74 milliamps, and the angle is 0, right, minus 67.5 degrees. So therefore it's equal to 17.74 angle 67.5 degrees milliamps. So that's the answer. Okay. If you draw a phasor diagram, you would have, well, this is your VS, your V. Did I write VS or just V? Or did I write anything? Okay, just write VS here. Okay. So VS here, okay, is 10, right, 0 degrees. And the current, right, is 67.5. So 67.5. Sorry, this should be smaller because it's 1.74 milliamps. Okay, so this is your I and this is your V. So you can see that since you have a capacitor in your circuit, the result is that your current leads, right, ICE, your current leads the voltage by 67.5 degrees. Okay, so that's how a simple analysis. Okay, I want to point out to you something is that your set total. Okay, your set total. Okay, your set total now has, see, it has 2.2 minus J 5.3K ohms. Your impedance, okay, consists of both. When you have a combination of resistor and capacitor or inductor, your impedance would consist of the real part and the imaginary part. Okay, so in general, your impedance consists of the real part and the imaginary part. And we write it like this. So R is the resistive component. X, we call it the reactive component or reactance. Okay, so therefore XL, reactance for inductor, is equal to omega L. Okay, and your XC, ohms, is 1 over omega C. Okay, if you take the reciprocal of the impedance, it's called Y. This is called the admittance. And the admittance consists of the real part and the imaginary part also. Right? So G is called the conductance. And B is called the susceptance. Okay, so impedance consists of the resistive component and the reactive component, X. So this is a new term you have to know. Okay, X is called the reactive component or reactance. Okay, so from now on, okay, in AC we will deal with impedance, and all the rules of circuit analysis you have learned before applies. Okay, so for example, the dividers, if you have impedance connected in series, Z1, Z2, Z3, right? This is Vs. Okay, if you want to find Z total, looking from the voltage source, you can see that the current flow through all three, the same current, so they're all connected in series. So Z total is Z1 plus Z2 plus Z3. As the current passes through all this impedance, of course it results in a voltage drop in each one. So V1, V2, V3. KVL still hold, KVL of this loop. Okay, so it's Vs would be equal to V1 plus V2 plus V3. And V1 is, so Vs is of course I times Z total. V1 is equal to I times Z1. V2 is equal to I times Z2. Just as if you are using Ohm's law. Okay. And if you have a loop, and you want to find the voltage drops in each one, you can use voltage divider in each of the impedance. So it implies that, okay, Vx then is equal to Zx over Z total times Vs. So therefore, if you want to find Z1 is equal to, if you want to find V1 is equal to Z1 over Z1 plus Z2 plus Z3 times Vs. So everything applies. okay, that you have done before. Or if you have in parallel, impedance connected in parallel. In parallel, you have IS, okay. Current comes out, divide into I1, I2 in each branch, I3, okay. Set total, you're looking from here, set total from the source, you will see that they are in parallel. So set 1 parallel with set 2 parallel with set 3. You use a formula just like a resistor. It's 1 over set 1 plus 1 over set 2 plus 1 over set 3. Okay. KCL still holds. So KCL, right, at this node would be, well, IS equal to I1 plus I2 plus I3. And the current I1, I2, and I3 are divided out from IS, so we can use current divider. So current divider, okay, so IX equal to set total over set X times IS. So you want to find I1, right, I1, it would be 1 over set 1 plus 1 over set 2 plus 1 over set 3 times set 1 times IS. Everything holds if you have two impedance in parallel, set 1 and set 2, right? And you have a current IS, current flows, divide into I1 and I2 like this, okay. Of course, set total is set 1 parallel set 2 is set 1 times set 2 over set 1 plus set 2, just like resistors, okay. We did for current divider, we did sort of like a shortcut formula. If you divide your current into two branches, right, two branches, we wrote it as, if you want to find I1, right, I1, right, it should be, well, if you use the original formula, it would be set 1 times set 2 over set 1 plus set 2, right, divided by set 1 times IS. So set 1 cancel, so you end up with the other set 2, the other, impedance in another branch that you want to find, divided by the sum of the two impedance in those branches, right? So therefore I can write it right away. If I'm not going to do all this here, I can write it as I2 would be, or I2 here pass through set 2, well, I'm taking set 1. So I'm taking set 1 divided by the sum, okay, the sum of the elements in the two branches, and multiply by IS. So my shortcut formula for current divider divided into two branches only, okay, right. So also in this case, sorry, let's go back. In this case, if I want to find Y total, your admittance, okay, it can be written as simply, right, Y1 plus Y2 plus Y3, just in case you want to use it, okay, in terms of admittance. So this is it for the topic of impedance. It's a very important topic, several formulas for you to remember, short but several, okay, like the formula for all the impedance, okay, right. So that's it for today. Thank you for listening to me. Thank you. Bye.